Alright guys, we are back talking about statistics yet again, and this time we're revisiting the idea of hypothesis testing. So a previous tutorial we talked about hypothesis testing when we knew the population standard deviation. Now, we're going to follow the same idea, but here we have a little bit of different context, because here we're only given sample data. We don't really know anything about the population, except that we're assuming the population is normally distributed. So let's dive right in. A past study claimed that Americans spent on average 17 hours per week on leisure activities. We want to test this claim. To achieve this goal, we take a random sample of 12 Americans and inquire about the amount of time spent on leisure activities. Their responses are listed below. Okay, then we have 13.6 hours, 14, 24.5, all the way to 21.4, and numbers in between. Assume that the amount of time spent on leisure activities assume that the amount of time spent on leisure activities of all Americans is normally distributed. That's very important. Using a 10% significance level, can we conclude that the average amount of time spent by Americans on leisure activities has changed? And then, of course, we are going to change it up a little bit and say, does this result change if we change the level of significance from 10% to 5%? So, the general idea of significance testing, of hypothesis testing, is not any different than the previous tutorial when we were talking about when we did hypothesis testing, when we knew sigma. The difference is right now we don't know sigma, so we're going to have to estimate sigma using the sample standard deviation. Now you notice here we don't have a sample standard deviation, we don't have a sample mean, all we have is raw data. Okay? Now that is that's going to take a little bit of work to find those sample statistics. So let's dive in here and figure this thing out here. Okay. All right. So when we are doing hypothesis testing, we know we need a couple things. We know we need some sort of standard deviation, and we know we need some sort of mean. In this case, they're both going to be sampled based on the sample, because all we have is sample data. We don't know anything about the population except that it's normal. Okay, so we have to calculate the sample mean and sample standard deviation from this set of 12 data points. Okay, now this is going to go back to, again, we have to go way back to figure out, to revisit the formulas for mean and standard deviation of a sample. But lucky for us, mean is easy. Okay, that's just x bar, and we remember that x bar, that's just equal to the sum of x over n. That's just the simple arithmetic mean there. Now, let's see. I should probably go ahead and calculate this. I didn't do this beforehand. I'm going to do this all in a candid manner. So let's see what we get here. So we have 13.6 plus 14 plus 24.5 plus 24.6 plus 22.9 plus 37.7 plus 14.6 plus 14.5 plus 21.5 plus 21 plus 17.8 plus 21.4. Okay. Right, I get 248.1. And again, we're gonna see how my calculator skills here work with not punching in any errors. So 248.1, and then of course how many items are in our sample? That is 12. Okay, so let's see what that equals. 248.1 divided by 12, and I get the sample mean to be 20. Let's see, 675. we'll keep those 3 decimals for now. Okay, now the standard deviation, that is a little more tricky to come by. It's not hard, it's just arithmetic, but it does take a little bit of work. So let's see here. See if I can get a different color for us. There we go. Okay, different color here for us, and let's do the let's calculate the sample standard deviation. Now, the symbol for that is S. Okay, or sigma. Usually Greek letters. Those are going to be your parameters, population parameters. The x bar and the s and s squared. Those are going to be your sample statistics. So if you remember the formula for the sample standard deviation, it looks bad, but it's really not too terrible. It's just arithmetic. So it's a big radical, and then you have, let's see, if I remember right, n minus 1 on the denominator. Then you have the sum of the x squareds minus the sum of x squared divided by n. Now hopefully I remember that right, but I think that's good. Okay? Again, I'm not cheating here. I'm not looking at a solution guide or anything. This is all candidates. Let's see what we have here. We already know the sum of x's. That was 248.1. Okay, we know n is 12, so we're good with the denominator here. That's going to be 11 there. But we need to calculate the sum of the x squareds. Okay, so that's just, it's not hard. You just have to square all of your data points and add them up. So again, I'm going to take a sec to do that. We had, let's see, 13.6 squared plus 14 squared plus 24.5 squared plus 24.6 squared plus 22.9 squared plus 37.7 squared plus 14.6 squared plus 14.5 squared plus 21.5 squared plus 21 squared plus 17.8 squared plus 21.4 squared. Okay, so I get the sum of the x squareds, that is squaring all x values and adding them up. Let's see here, let's get that big radical again. That is 5,633.53. Okay, then subtract off. Okay, we already know what the sum of x is. So we need to take the sum of x, square it, and divide by n. So the sum of the x's is 248.1. We need to square it, and then divide that by n, which is 12. Okay, I get 5,129.4675. Okay, let's extend that a little bit. Then we're dividing on the denominator by n minus 1. N is 12, so divide by 11. So let's see what that equals. Okay, so we have, let's see here, we have 5,633.53 minus that previous answer, 5,129 and change. Take that difference, divide by 11. Then we're going to take the square root. Square root of the answer, and I get 6.7693302. Let's just go there. Okay, I think that's enough. Okay. Oh, what the heck? It's only 2 more digits. 5,8. No sense in not putting those there. Okay, so there is S. That is our sample standard deviation. Okay. Now we're getting some of the work out of the way. We're chugging along here. So what we want to do now is, now of course, it's kind of funny. Now we're to the point where you usually are starting with most exercises. Most exercises you're starting that you have an X bar and you have a sample, either a population standard deviation or you have a sample standard deviation that's given. So here we had to calculate those on our own. So now we're pretty much to the starting point of most problems. So we need to talk about the 4 or 5 really, the 5 steps of hypothesis testing. These are the same as we did when we were using when we knew sigma and we were using the Z charts. Okay, so let's see here. Let me change colors. Let's see here. Let's go green. Yeah, that looks good. Okay. So step 1. Step 1 of hypothesis testing. That's basic. That is to state your hypotheses. Okay. Now, just like before, we had an null hypothesis and a alternative hypothesis. Now, what are the hypotheses here? Well, the null hypothesis, that's the status quo. That's the one that assumes things today are the same as they were are the same as the results that were found in the last study. The last study, let's see here, found that Americans spend 17 hours a week on leisure activities. So that defines our null hypothesis. Remember, that is H naught. Okay? H naught, H sub 0, that is that mu equals 17 hours. Okay. Now the alternative, that's what we have to kind of read the text to figure out what we should make the alternative. It's either going to be mu is greater than 17, mu is less than 17, or a combination of both, mu is not equal to 17. So let's read here. Using a 10% significance level, can we conclude that the average amount of time spent by Americans on leisure activities has changed? So notice there, it doesn't say is the amount of time, the average amount of time less than it used to be, or is it more than it used to be? It just says, has it changed? So that indicates to me that our alternative hypothesis, again, sometimes it's labeled H sub 1, sometimes H sub A. Again, I kind of like using H sub 0 and H sub A because then you can remember ho-ha is the first step. I just think that's kind of funny. So, again, a lot of times a book will use H sub 1 right here. So, all we want to do is see if it's changed, if we have enough data to conclude that it's likely that the mean has changed. So that just means we're going to say, is the mean not equal to 17? Okay? That's the alternative hypothesis here. Okay? And that's step 1. Done. Okay? Now remember, just to label here, that is the null, and that is the alternative. Okay? Now, that takes care of step 1. Now, step 2 is to select the distribution. This is the easy part, and I've already told you twice. The whole point of this video is that we're only given sample data. When you're only given sample data, that means you don't know the population standard deviation. Okay? So, let me rephrase. We're given the population mean. That's what we're comparing here, but we don't know sigma in regard to the population, and that's what's important. That's what's going to make us have to use the t-distribution. And again, for our purposes in this class, we use for our examples we use either t or z. When you get into more advanced stats, there's other distributions, but we're just using t or z. So the moral of this story is since we only have S and not sigma, we have to use the I should say students t distribution. Okay, that's what you have to do whenever you want to, whenever you need to do a hypothesis testing and you don't know the population standard deviation. Okay? Alright, so we're going to use the t-distribution. Okay, so that's the big difference between my last example, my last tutorial, and this example. So that's step 2. Pick our distribution. Now, the third step is going to be to determine the rejection region. Now, my last video, I called that essentially drawing the null model. So we want to draw the null model. We want to define our rejection regions. Now, I'm going to go over here. I think I'll have enough room over here. Okay, so we want to draw the rejection regions. Now, we can do that based on p-values if we want to, or we can do that based on critical values. We're going to talk about both here. Okay, so let me draw a curve. Okay, it's not the most pretty normal curve you've ever seen, but it gets the job done. Here, I'll fix this a little bit. Let's see if I can make that look a little better. Maybe. Yeah, a little better. Okay, alright, so there is a curve we can work with. Okay, now, if this is the null model, okay? If the null model, if the null hypothesis is true, this is, again, assuming the null hypothesis is true, what is the mean? Okay, well, the mean, right here in the middle, is 17 hours. That is assuming the null hypothesis is true. Okay, now, how do we get our rejection regions? The rejection regions are based on the level of significance. So to start with, we want to use a 10% level of significance. Okay. Later on, we'll draw a different model where, or we'll talk about the 5% in a little bit. But right now, we're just doing 10%. So now the question is, where do we draw? What are our critical values if there is a 10% significance level? Now, remember, this is a two-tail test. A two-tail test is when your alternative hypothesis is not less than or is not greater than, it's not equal to. So that means we're dealing with both tails as far as our rejection regions go. Okay. So now here's the question: if there's a 10% significance level, that means that 10% is going to be in both tails. Now, of course, you know that this is a symmetric distribution, and I'll just go ahead and fix that a little bit. Yeah, so my picture is obviously not perfect, but there's the equal amounts of area under the curve in the left-hand side and in the right-hand side. Okay, equal amounts of area under the curve. Now, 90% is centered around the mean here, okay, because we're using a 10% significance level. So this is pretty similar to what we did when we were talking about confidence intervals. There's 90% centered around in the mean here. That means 10% is on either side. Okay, so let's see here. This is 0.90. Now, if there's 0.1 here and here, how much is on both sides? If you know there's symmetry, and so there must be equal amounts on each side. Okay, well, I think that means there would have to be Well, if you want to use your, if you want to think about it, you do, here's the calculation, you do 1 minus, okay, remember, 10 is, I guess we should say more formally, alpha is 10%, which is 0.1. So to figure out the number there, you can do 1 minus alpha, which is 1 minus, oh, sorry, I just messed up. I was thinking confidence intervals. So I take back the I take back the last 10 seconds. What you want to do is, okay, if there's 10% there, well, how much is it on each side? Well, there's 0.1 divided by 2, and it's 0.05. So 0.05 there, and 0.05 there. Okay, that's the area. That's our probability p level on either side of those tells. Okay, so it turns out if we go and calculate our test statistic, and it falls over here, that's our rejection region. Now, what we want to do is figure out what t-value is right there. That is, what's the t-value that separates rejection region from non-rejection region? So I should label this non-rejection. And so those, by default, would then be rejection regions. We want to figure out what t-value goes here and here. Now, remember, when you look up the t-chart, our t-chart is always based on, you want to find the area in the curve to the right of t. So we are going to look at the 0.05 column, but which row do we look at? Remember, rows are based on degrees of freedom. So here, degrees of freedom, and when you're dealing with the t distribution, degrees of freedom is n minus 1. So specifically here, n minus 1 is 11. Okay, so if we go to the t-chart, and I'm going to look this up real fast, so give me just half a sec. If I go to the t-chart, I'm looking at row 11 for degrees of freedom. Okay, so row 11, and I'm looking at the column with 0.05. So if you look at the intersection of the 0.05 column and the row with 11, I get 1.796. 1.796. So t crit, it's our critical point, equals 1.796. Make sure I've said that right. Yeah, 1.796. These are our critical values. So negative 1.796. Because over there, because we have this nice symmetry. Since the t distribution is a family of approximately normal distributions. Okay, so again, that is t crit. Those are our critical values. So there's two ways we can think about this. The next couple steps. Okay, so we have set up a null model here. If it turns out that our test statistic falls over here in this rejection region, we'll know that because the t-value associated with that observation will be greater than 1.96, or the p-value associated with that observation will be less than 0.05. Okay, that's how we're going to make that decision in just a few minutes. So that's step 3. That's, again, we constructed our null model. We labeled the rejection regions and the non-rejection regions. We found our critical values and the p-values. Okay? Now, let's go to step 4. Step 4 is where we calculate the test statistic. Okay? So then here we're using the t distribution. So this is where we calculate t. Okay? Now, lucky for us, t, for all practical purposes, is calculated in the same manner as z. The difference is the underlying distribution is fundamentally different. Okay, it's approximately normal for large degrees of freedom, but it is an approximation to the standard normal. So, T, again, here is x bar. Now that is the average of our sample average, sample mean. What was that? 20.675. So we take 20.675, subtract off mu. Mu was up here, 17. Okay? So subtract off 17. Now, we need to divide by our standard error. Now, remember, standard error is not just standard deviation. Standard error is the standard deviation of our sampling distribution, which was the sample standard deviation divided by the square root of n. Okay, so we actually need to take that value. I'm going to not write all the digits since it's so long, but I'll use those digits when I make the calculation. So I'm going to say 6.769 divided by the square root of n, and n here was 12. Again, I'm not rounding that for practical purposes of calculation. I'm just shortening when I wrote it right there. Okay, so let's see what this equals. Okay, so 20.675 minus 17, okay, divided by, make sure to be careful here with you when you're using a calculator. We have 6.76933,258 divided by the square root of n, which is 12. Okay, so I get that is equal to 1.88 for a t-value. Now, t-values, we actually round to 3. If I round that to 3, it's 881. So there is my t obtained, or t observed. Okay, that is what we found. That's the test statistic we found when we took that sample of 12 people. Okay, so that was step 4. Okay, now let's in step 4 we actually need to figure out where this falls on our distribution. So let me change to. Let's just go to purple. Okay, where does this go on our distribution? Okay, well, if you look over here, it looks like our critical value is 1.96. So a t-value of 1.81 falls to the right. So I'll label it there. That is t equals 1.881. Oh, that is t. Oh, let me fix that. T observed equals 1.881. Now, you see that t-value fell in our rejection region. Okay? It fell in that shaded part. So, according to, remember the convention that if t observed was greater than t critical, then we reject the null. Okay? Oh, we're actually getting into step 5 here, but that's all right. That's all right. Okay. Now let's just go ahead and say that we're on step 5. Sorry, you know these get blurry here sometimes. So step 5. Oh, let's be a little more neat. Step 5. Okay. So we need to make a decision, and that is we reject the null since that happens. Okay, because t observed was greater than the critical value for our null model. Okay, what that means is that this was an unlikely result if our null model was true. So it was unlikely that the average amount of leisure time spent by Americans was 20.675, it was unlikely that happened by chance alone, that was due to sampling error. It's more likely due that that the overall amount of leisure time has indeed increased across the board, and that the population mean is actually higher. Okay, so we reject the null, and it is likely that the alternative hypothesis fits the observed data better than the null hypothesis. So we reject the null hypothesis. It appears that the alternative hypothesis, that there is a change, that there has been a change in leisure time, it appears that that is more accurate. Now, let's go back here. I want to talk about the p-values here. Okay, so I showed that we could reach this conclusion by observing, or by noticing that the observed t-value was greater than the critical t-value. So we reject the null hypothesis. Now, what about the p-value? We could also find the p-value that's associated with an observed t-value of 1.811. Now, how do you do that? Okay, let's see here. If I'm going to get a little more room laterally, go like this. Yeah, here we go. Okay. What about, how do we calculate the p-value associated with that t-value? That is, what is the area to the right of that purple t-value? Okay. Well, let's look in the back of our book to see. Now remember, we are talking about a degrees of freedom of 11 still. Again, this is the null model we're talking about, degrees of freedom of 11. And we want to know what's the area beyond 1.881, a t-value of 1.811. So let's go back here. Give me a sec to look at my chart. Again, degrees of freedom 11, and I find that if I look at a t-value of 1.881, I don't find 1.881 exactly. I see 1.363, 1.796, and 2.201. So I don't have an exact t-value in my chart of 1.881. But what you can do is assume that the looking at our chart, we can say that our, let me go back to purple here since that's what we're working with, that our observed t-value, so t observed, is between two values that are in my chart. The ones there between, again with degrees of freedom of 11, is 1.796 and the other one is between 1.796 and 2.201. So that's the best I can do as far as finding a 1.881 in the chart in the back of the book on the degrees of freedom 11 row. So I need to find the p-value associated with these two guys. Okay? So this is going to tell me what my p-value is approximately. So I can't find the exact p-value without a calculator or a computer, but using the table in the back of the book, I can find a range of p-values. Like I can say the p-value associated with my observed t-value is between this and that. So what are those two p-values? Oh, let's see here. Degrees of freedom of 11 here is 0.05 and 0.025. So 0.05 and 0.25. Okay? All right. So let's see here. Now, if you do this, we can see that that the p-value lies somewhere between 0.05 and 0.25. Now, so what's the worst case scenario for my p-value? The worst case scenario and remember, this is a two-tailed test. So whatever p is, you have to multiply it by 2 and see if that's less than alpha. Okay? So over here, if you multiply 0.05 by 2, that's the worst case scenario for my p-value. That is oh, you know what? I need to look at my chart. Yes, I'm missing a 0 over here. I thought that looked funny. So let's see, eraser. Notice here, I forgot a 0 right there. I was about to multiply and then it was not working out. Okay, that's 0.0025. Okay, so the worst case scenario, if p is oh, then when I change that, let me reverse these signs. Sorry guys, that's what happens when you're being candid. Obviously, 0.05 is greater than 0.0225. So this should be reversed. Either I can reverse the signs, or I can just reverse where the numbers are. So I'll just reverse where the numbers are. That's fine. That happens sometimes. Alright, so we have 0.025 and 0.05. So look, here's what happens. Since this is a two-tailed test, we need to double these values. So p can range, because this is what p is only over here. So the area to the right here is somewhere between 0.025 and 0.05. Now, I already know that I'm going to reject the null hypothesis because my t-value is beyond, my t-observed value is beyond my t-critical value. So, but let's just see what happens here. So, p at the very highest is 0.05 times 2. Now, what's 0.05 times 2? 0.05 times 2 is 0.1. Okay? Now, what's the smallest p is going to be? Well, that's 0.025 times 2, which is 0.05. So, when we're talking about the area, okay, so if I find negative t over here, my negative t observed, and I find the area to the left of that, so that's, since we're doing a two-tailed test, we have to find the area in both tails. So that would be negative t observed. If I add those two purple shaded portions up, it's going to range somewhere in between 0.05 and 0.01. Okay, P for two-tail test. Okay. Now, what do you notice about this? Okay. Now, again, we've already reached our conclusion using the critical values, which is the way I prefer to do this anyway. But since on some of your homework and some of the examples in the book, they use both approaches, the p-value approach and the critical value approach, I'm going to show you both. So, at the highest, our p-value is 0.01. Well, what's alpha? Okay. If the worst case happens and we don't know and we didn't compare critical values, we would say it could be possible that that p is not less than alpha. Again, right there, at the very worst, p equals alpha, which we want p to be less than alpha to reject the null. Okay? But over here, p is certainly less than alpha, because alpha is 0.1 and 0.05 is certainly less than 0.1. Now, so if we were just doing this calculation based on alpha, we couldn't make a good decision. Now, it's likely that since the highest end of the range is 0.1, that we would still be good, because the low, you go from at alpha to below. Okay? But that's very close to alpha. And again, you want an alpha smaller than, you want a p-value smaller than alpha. Okay? So that is, how you would have to evaluate using p-values. You have to find a range for p, because in the back of the book, using that chart, it's unlikely that when you find an observed t-value, that's going to be an actual number in one of your columns. Oftentimes, it's a number that falls in between two columns. And so you have to find a range of p. So we know that p is somewhere between 0.05 and 0.1, but there's just the p-value approach, we don't know where that is. Now, if you have software or you know how to use your TI calculator, you can actually find an exact value of p for a t-value. And maybe I'll show you that in class one day. But just using your chart, as the book shows you how, this is how you'd have to find the p-value of an observed t statistic. But that's why I prefer to find the critical value way, because you don't have to worry about this range. All you have to do is find, is the t observed, is that beyond the t critical, or is it not? Is the t observed over here close to the mean? If it's over here close to the mean, then it's probably not the case that we should reject the null. In fact, if you're close to the mean, within a certain distance of 17 in this case, then that probably happened just due to regular old random sampling error. Because if you look at the sampling distribution of this null hypothesis, you would expect, if you took every possible sample of 12 Americans and asked them how much time they spend on leisure per week, and then graphed all of that data, you would found the mean of that every sample and graphed it. You would expect a lot of samples to have to be close to the mean. Like you'd expect, maybe 18, maybe 17.5, maybe 16, 16.5, 16.1. You'd expect a lot of samples to have a mean around, to have a sample mean around the population mean. But if you calculate, like we did, we took a sample of 12, we calculated the mean, and it was way up here, far away from the mean. We can conclude that that is not very likely. In fact, we find the probability of that is between 0.1 and 0.05. So maybe 5 times out of 100 we would get that result. If we took 100 samples, 5 out of that 100 samples would have a t-value at or above 1.881. Which that t-value corresponded to an average of, what was that average? Sample average of 20.65. So 5 out of every 100 random samples would have a sample leisure hours per week of 20.675 or greater. 5%. That means 90% would have less than. Okay, so that is hypothesis testing here with a t-distribution. Again, we use the t-distribution because we didn't know sigma. So let's just review really fast. Okay, we had a study here that said Americans spend 17 hours a week on leisure activities. We said, hey, We want to know if that's true or not. So let's take a random sample of 12 folks and calculate their sample mean. Okay, how much time they spent on leisure. Well, we did that and found they spent 20.675, which is, over, almost 4 hours higher than what the previous study had said. Okay, so we want to know, is that a fluke? Did that happen just due to random sampling error? Or, or is it due to the fact that there is a trend that people are spending more time on leisurely activities than they were when the previous study was conducted? Okay, so what we did was, with this example, we weren't given a standard deviation for the population. In fact, we weren't given the mean for the sample either. We were given a population mean, and we were given some sample data. So over here we had to calculate the sample mean. We got 20.675. We had to calculate the sample standard deviation. That was, using, if you're looking in our book, that was chapter 3. This is what we call the shortcut formula. It's not really the like the definition, the traditional definition type formula, but it doesn't take as long as the other one does. Okay. We then stated our two hypotheses. The null hypothesis is that there's no change. Is that the population still spends 17 hours per week on leisure activities, but the sample we got was just a fluke, random sampling error, because it certainly is possible. I mean, it is just not very likely. Okay. Now, alternative hypothesis is that there is a change. There is a difference now compared to what was going on when the past study was conducted. Okay. Step 2 down here, we determined that we use the t-distribution. That is due to the fact that we don't know sigma. We had to compute S and use S to estimate sigma. So when we do that, we have to use the t-distribution. Over here, we drew our null model. Our null model is assuming the null hypothesis is true. What would this look like? What would our critical values be? Shade the rejection area, and then label rejection area, non-rejection area, that kind of stuff. Okay. Step 4 down here, that was to actually compute our observed value. Again, this is a t-statistic, but it's computed practically in the same way that the z-statistic was. You take your observed sample mean, subtract off your population mean, then divide by the standard error. Okay, we get 1.881. That is our t observed. We then plot that observed value. Color code here. Observed value. Okay, our observed value, we plotted over here. We notice that our observed value is greater than our critical t-value. And since that's the case, again, this is what we've talked about before, if your observed value, your observed statistic, is greater than your critical value, that means you reject the null. Okay? That's one of the ways to determine you reject the null. Then afterwards, we talked about how to reject the null based on p-values. Okay, so we found the p-value associated with this observed value was in the range of 0.05 to 0.1, which that's getting close to non-rejection, or is at the boundary of non-rejection. But since we had already made the reject the null conclusion based on the critical value, we were good to go. Okay, but usually we want to make sure that this range is well within, well below alpha. Okay, well below alpha, not equals alpha right there. Okay. All right. So since we decided to reject the null, what that means is that there probably is probably the null model is not good at describing the sample we found. That the sample we found, the mean we found of that sample is not very likely to happen if the null model was true. Okay, so we reject the null and reject the null, and we conclude that the alternative hypothesis fits the data better. Now, I almost forgot. I was about to say see you later, but I almost forgot. I actually up here said, what happens if you change the significance to 0.05 to 5% instead of 10? Real quick. If I go up here, I'll just draw another picture real fast. So I need to keep that observed value. I'm going to draw just this in another color. I'm going to draw another null model. Okay, but now this null model is going to, again, we're assuming there's no change here, but I want to have, obviously I'm going to have a different rejection region, because now I said the rejection region, the level of significance is 0.05. Okay, so if it's 0.05, then how much data is here in the middle, the non-rejection region? Okay, well, the non-rejection region is 0.95 if the level of significance is 0.05. So that means here and here, both tails together, is 0.05. So 0.05 divided by 2, that means there is 0.025 area under the curve there, and 0.025 area under the curve there. So I want to figure out what these two critical values are. Okay, so T critical right there, and T critical right there. What are those? Okay, so again, I go back to my book, again, real fast, back to your book. Again, we have degrees of freedom is 11 still. Call sample size is 12, n minus 1 is 11. And we want to see the right-hand critical value. We're looking at the column 0.025. 0.025, column intersected with the row of 11. It's 2.201. 2.201, which would then mean that is negative 2.201. Okay? Alright, so those are our critical values now. But look at our observed value. Again, I'll go back to purple for my observed value. My observed value plotted on your null model. Okay? Your critical value is less than T observed is 1.881. See how the critical value is greater than the observed value? So T observed is less than T critical. Okay? Since my observed statistic is less than my critical statistic, the conclusion is we fail. I failed to write too, but specifically fail to reject the null. Okay? Fail to reject the null. Because my observed value is less than my critical value. Now, we can go back again. Let's go over here, and we have alpha. Alpha here was 0.05. Okay, so that's alpha. If we scroll over here, what was our range of alpha we found? The range we found for alpha was at the least 0.05 and at the most 0.01. So if we go back over here, and we know that the range of of P, we said was at the least 0.05 and at the most 0.1. Oh, I can't even remember now. Yes, 0.1. I was right. Okay? That means at the very least, our p-value is equal to alpha. And at the and that's best case scenario, if we're just working off p-values. And then it gets bigger from there. So since p is greater than alpha, we also know we must reject the null. Okay? So, two ways to know we reject the null or not reject the null. Oh, we must, let me just erase. Since p is greater, we fail to reject the null. That was a fail. Speaking of fail, we just fail to reject the null. Sorry, guys. Fail to reject the null. What that means is the sample we found is pretty likely if our null model is true. Okay? Now, again, so we changed the level of significance. We changed the bar. We lowered the bar, essentially. We raised the bar. We said, instead of, for every 100 random samples, we would expect that result 10 times. Let's say with every 100 samples we collect, random samples we collect, we would expect that result 5 times. So we lowered alpha, which was essentially raising the bar, so we would fail to reject the null, which would mean that sample mean of about 20 we found would be likely given an alpha level of 0.05. So see how our conclusion changed based on our alpha level. Okay. Now, you might think that's funny, and it is funny. There's lots of controversy over this because people you change alpha and your result changes. The idea is for a large t-value or a large z-value that's very far away from the mean, whether it's very small or very big. If it's very far away from the mean, we need to figure out what's going on. So, as far as the conclusion changes when you change the p-value or the alpha value. That's one of those things that alpha needs to be set. A high standard needs to be set for alpha, and then the moral of the story is if you have a value that's far away from the mean, we need to figure out what's going on. It could be sampling error, it could be non-sampling error, or there could be a trend. So if you get a high, if you get a result, observed t-value that's pretty high above your critical value, then you need to see what's going on. But I mean, there could be many different reasons for it. And again, a lot of this has to do with methodology and all kinds of stuff like that. So, but as far as we're concerned, this is what we're dealing with now, just getting the basics down. So, to recap with this last little bit, when we changed alpha, the result, their conclusion changed. That is, before we rejected the null because our observed t-value was beyond our critical value. But when we changed the level of significance, we changed alpha, all of a sudden our observed value was less than our critical value, which means that we fail to reject, which means we retained the null hypothesis, which if you retain the null hypothesis, that means there no change, occurred. Let's say no difference has been observed. That is, when they did the study a couple of years ago and found that the amount of leisure time was 20.675 or something, even though we took a random sample and got, in that particular sample, a higher mean amount of leisure time for those 12 people, it was probably just due to chance, due to sampling error. That is, we took a sample of 12 instead of taking the population of every American. So we cannot conclude that there has been any statistical difference. Okay. All right. So I think I've talked about as much as I can about this particular exercise. If you guys have any questions, as always, feel free to ask before class, after class. Send me an email, swing by my office. I hope this has been helpful. Let me know if you need more help.